Welcome, everybody. Today we have a great topic to talk about, which is zero trust approach to enterprise Kubernetes deployment. On the agenda today, we have why container security is so important and the risks and challenges around it. We'll start at high level on container security in general. Then we'll have a look at zero trust and how we can apply zero trust principles to Kubernetes deployments. And in the end, we'll wrap up by diving into how D2IQ Kubernetes platform products ensure your deployments are secure. Containers are ideal for application modernization and hybrid multi-cloud scenarios because they are lightweight and portable. As companies began embracing containers, often as part of modern cloud-native architectures, the simplicity of the individual container began colliding with the complexity of managing hundreds, sometimes even thousands of containers across a distributed system. To address this challenge, container orchestration emerged as a way of managing large volumes of containers throughout their lifecycle. Enter Kubernetes. As cloud-native technologies like containers and Kubernetes mature rapidly, they are becoming the preferred way to build new software experiences and modernize existing apps at scale and across clouds. According to the recent reports, over 86% of organizations manage some portion of their container workloads using Kubernetes. However, security still remains a large concern. In the same survey, over half of respondents stated that their organization does not have an adequate investment in container security. Without a strategy in place, this can quickly cause delays in adoption of Kubernetes or serious security incidents even. While Kubernetes is growing in popularity and its use within organizations is maturing, at the same time, security concerns around Kubernetes are mounting. A Red Hat survey of Kubernetes adoption and security showed that of 500 DevOps professionals surveyed, 55% delayed an application release due to security issues. 94% experienced at least one Kubernetes security incident in the past year, and 59% said security is their biggest concern with regard to continued use of Kubernetes and containers. Some challenges we face around security in Kubernetes and containers in general is that beyond basic features such as enforcing role-based access control, Kubernetes does not offer the ability to protect applications from vulnerabilities. While cloud practitioners are armed with best-in-class knowledge, support, and security practices, it is statistically impossible to have a common security posture for all cloud instances worldwide. Attackers know this and use it to their advantage. By applying evolved tactics, techniques, and procedures, attackers are exploiting edge cases. As a result, organizations like Capital One, Jenkins, Docker, and many others have experienced high-profile breaches. Let's have a look at some major Kubernetes security incidents that have happened in the past. Capital One security incident was a big one and forced a lot of people to wake up and take notice. This breach saw 30 GB of credit application data affecting about 106 million people being exfiltrated. What actually caused the breach is something we see quite a lot of in the world of Kubernetes, a misconfiguration. Microsoft, after disclosing that there was a large-scale crypto mining attack against Kubernetes cluster in Azure in April last year, uncovered a similar campaign in June last year that targeted misconfigured Kubeflow containers to turn them into crypto miners. Automaker Tesla was one of the earlier victims of cryptojacking when a Kubernetes cluster was compromised due to an administrative console not being password protected. Around the same time as the Tesla incident, hackers managed to exploit a vulnerability in Jenkins to cryptomine to the tune of about 3.5 million in 18 months. In case of Docker, attackers managed to plant malicious images in the Docker Hub last year, causing anyone who uses those images to be cryptojacked. What this means is users unknowingly deployed cryptocurrency miners in the form of Docker containers that then diverted computing resources toward mining cryptocurrency for the attacker. Kubernetes security incidents are growing because the attack surface is now an infinite army of hybrid clouds, on-premise data centers, IoT devices, personal computers, edge devices, and more. Closed-minded security is dead. Gone are the days where you could just focus on your application and leave the rest to a firewall. A threat could potentially come from a service being used by a service that's then being used by a service that you are using. We'll see some of the major risks that Kubernetes production deployments face and go through each one of them in detail. Compromised images and image registries. So to ensure the security of images, organizations should implement strong governance policies that ensure images are securely built and stored in trusted registries. For example, organizations should make sure that container images are built using pre-approved and secure base images, which should be regularly scanned for issues and vulnerabilities. Organizations should create a list of registries that are allowed for use to standardize this process. And images should always be scanned before being used to create containers in order to avoid tampering. Compromised containers or malicious traffic. Containers and pods need to communicate with each other as part of normal operations. However, this communication can be exploited by threat actors. A breached container can affect other containers and pods. And to ensure communication is secured, organizations should put in place network policies that limit communication to the minimum necessary for workloads to function. This includes both north-south traffic, which is ingress and egress, and east-west traffic within the cluster. Network policies should be automatically adjusted to ensure they do not hurt productivity. Lack of visibility. Visibility is critical to ensure security is maintained. However, it can be challenging to achieve visibility in such a complex, distributed, containerized environment. There can be a large number of containers scheduled, deployed, and terminated, all of which need to be tracked, monitored, and managed. The distributed and dynamic nature of a containerized workload makes it difficult to collect, track, and understand relevant metrics. Kubernetes can be deployed in multi-cloud or hybrid cloud environments. Each cloud vendor provides its own monitoring and visibility tools, and it becomes very difficult to allow consistent visibility across environments. Securing applications without visibility can be difficult or even impossible sometimes, without which it is not possible to detect critical vulnerabilities or discover misconfigurations before threat actors exploit them. Visibility is also critical to monitor containers at runtime to detect attacks and to keep track of containers that are no longer in use in order to properly retire them before they become a liability. Unsecure default configurations. Kubernetes is built to speed up the deployment of applications and simplify operations and management. While it provides a wide range of controls that can help organizations effectively secure clusters and applications, it does not provide secure configurations out of the box. For example, network policies in Kubernetes behave similarly to firewall rules, controlling how pods can communicate with each other as well as other endpoints. Once a pod is assigned a network policy, it is only allowed to communicate with the assets declared in the network policy. However, Kubernetes does not apply network policies to pods by default. This means that after being deployed, all pods can talk to all other pods within an environment. This makes it critical to ensure all cluster resources have appropriate security policies defined. And another concern is secret management. Secrets define how sensitive information like keys and credentials is accessed and stored. When managing secrets, it is critical to make sure that they are not used as environment variables or hard-coded within images. Secrets should be managed externally to containers with careful access control to protect them from unauthorized parties. And lastly, compliance challenges. For many organizations, compliance is a critical concern. Achieving compliance in a cloud-native environment is a highly challenging endeavor. To achieve compliance, organizations are usually required to implement certain security measures. This often requires enforcing best practices, benchmarks, and industry standards, as well as internal policies. In addition to maintaining compliance on a regular basis, organizations also require to provide proof of compliance. This requires visibility, monitoring, and logs, the data needed to perform audits. To ensure auditors have access to the data or systems, organizations need robust features that are not necessarily provided by plain open source Kubernetes. That brings us to what and how do we protect? Cloud native security is implemented across 4 key layers known as the 4 Cs by CNCF. Security measures that protect the code. For example, using vulnerability scanners and secure coding practices. Security measures at the container level. For example, restricting access to network ports and encrypting data in transit. Security measures at the cluster level, for example, defining network security policies and hardening all master nodes. And finally, security measures that protect infrastructure. This is usually implemented by cloud providers or on-premise IT staff. Having talked about the risks and challenges around Kubernetes security, let's see what is zero trust and how we can leverage its principles to secure our deployments. The term zero trust was popularized based on the realization that traditional security models operate on the outdated assumption that everything inside an organization's network should be trusted. Under this broken trust model, it is assumed that a user's identity is not compromised and that all users act responsibly and can be trusted. In this case, once on the network, users, including threat actors and malicious insiders, are free to move laterally and access or exfiltrate whatever data they are not limited to. Remember, the point of infiltration of an attack is often not the target location. In a trust but verify based model, what happens is we create concepts like trusted users and trusted network, but we actually don't do any verification because those people or that traffic is trusted. The zero trust model recognizes that trust is a vulnerability and eliminates the concept of trust within the network. It says that there are no more trusted users, no more trusted interfaces, no more trusted packets, and no more trusted applications. It is a strategic initiative that helps prevent successful data breaches by eliminating the concept of trust from an organization's network architecture. Rooted in the principle of never trust, always verify, zero trust is designed to protect modern digital environments by leveraging network segmentation, preventing lateral movement, and simplifying granular user access control. The basic idea behind zero trust is the assumption that all devices and users are untrustworthy until proven otherwise. Even after a user or entity is proven to be trustworthy once, zero trust model does not by default trust the same user or device the next time they are seen by the system. Trust in the zero trust model is never taken for granted, but is based on observation and regular authentication to help limit risks. So essentially, a zero trust approach aims to wrap security around every user, every device, every connection, every time. This model is built upon 3 fundamental assertions. The network, first one is the network is always assumed to be hostile. We always verify based on the assumption that external and internal threats exist on the network at all times. The second one is resources in the network should be securely accessed regardless of the location. We implement checks in a way where locality of the resource is not sufficient for deciding trust in a network. And the third one is every user, device, and all traffic should always be authenticated. In short, no person, device, or application in the enterprise network should be trusted by default, no matter if it's in the internal network or external network. The fundamental basis of the trust should be based on the access control using right authentication and authorization. The distributed nature of cloud-native computing architectures means workloads are running in different location and network, and often they are running across different clouds and on-premise as well. The old model of trusted networks that rely on perimeter security controlled by firewalls is based on flawed assumption that the attacker is coming from outside. If the attacker comes from inside, then this whole model falls apart. In today's world, where more and more cloud-native systems will be deployed on container-managed platforms like Kubernetes, a new solution is needed. We can leverage zero trust principles to secure container architect infrastructure by securing individually each one of those pillars of a container infrastructure. First one is GitOps. Most digital projects are used to working with GitHub and GitLab repositories. But moving to GitOps requires teams to really adopt a declarative approach to how code is pushed. Tooling like Flux helps to achieve the necessary deployment from Git into Kubernetes. As mentioned earlier, zero trust means taking a shift left approach to security and expanding into DevSecOps. Security operations cannot operate in a silo, and that means security teams must leave behind traditional ways of working and tooling and give importance to code source. Most companies are now only learning the complexities of managing and securing Kubernetes. Services like Istio that appear to be a standard in Kubernetes, given its ability to control traffic, security, permissions, can be used to implement a secure service mesh solution. Service identity should be implemented using certificate-based MTLS. Existing API and microservices architectures should be re-architected to implement a service mesh design. And policy management infrastructure is fundamental in managing whitelists and attributing level access controls. Automation and real-time auditing of each service identity is required. All these are challenges that need to be and should be addressed for an enterprise to deploy a zero trust-based architecture in a cloud-native environment. And now we'll talk about how D2IQ products strive to achieve secure deployments. D2IQ's Kubernetes platform, or DKP as we call it, security posture can be broken down into 4 concepts: securing traffic flows, access and identity management, logging, monitoring and compliance, and operating and maintaining the cluster. D2IQ Kubernetes platform, DKP, was designed to provide a fully interoperable and CNCF conformant Kubernetes experience, which ensures you always leverage the best of what the industry and community has to offer with Kubernetes. The technology footprint of DKP is composed of the following. Convoy is a comprehensive enterprise-grade distribution built on upstream open-source Kubernetes with the add-ons that are needed for day 2. Those add-ons are production-selected, integrated, and tested at scale, enabling a shorter time to production. Delivering new applications and services with an eye on rapid time to market is absolutely critical for most organizational initiatives. Further, maintaining an environment that provides reliability and performance in a day 2 operational environment is mandatory, even in the face of upgrades or continuous deployment of code and application components. As organizations leverage Kubernetes, they will require a stream of additional services which are necessary to support a production environment's need. These services can include functions such as logging, monitoring, networking, disaster recovery, load balancing, developer tooling, and visualization, among many others that will be a requirement. Kommander provides governance and lifecycle management of different Kubernetes clusters from a single management plane for viewing multi-cluster health, managing distributed operations, and leveraging operational insights for an enterprise's Kubernetes usage. Multiple project teams, line of business units, and functional groups can create and maintain domain-specific clusters while providing the enterprise's central IT organization with cluster operational visibility. Kommander enables cluster governance and centralized supervision without interfering with the day-to-day business functions and requirements that different clusters support. With Kommander, organizations can contain cluster sprawl to increase the security, manageability, and governance needed for enterprise-grade day 2 operations. In Kommander, there are 2 higher-order logical separation options: workspaces and projects. Workspaces give you the flexibility to represent your organization in a way that makes sense for your team and configuration. For example, You can create separate workspaces for each department, product, or business function. Each workspace manages its own clusters and role-based permissions while retaining an overall organization-level view of all clusters in operation. Projects empower teams to deploy their configurations and services to clusters in a consistent way. Projects allow central IT or a business unit to share their Kubernetes clusters among several teams. Using projects, Kommander leverages Kubernetes cluster federation, which is KubeFed, to coordinate the configuration of multiple Kubernetes clusters. As platform security, DKP goes through a rigorous testing and review process where it is scanned against CIS benchmarks, CVEs, and then deployed and soaked for upwards of 2,000 hours with mixed workload testing. D2IQ relies on upstream Kubernetes, which currently maintains community support for up to N-2 versions. This time period tends to equate to 9 months of upstream support for any given minor version of Kubernetes or a new minor release of Kubernetes about every 3 months. D2IQ can and has submitted enhancements and fixes for the underlying components, including in all platform and products. This work has included triage, root cause analysis, and fixes for upstream open source projects. Our engineering teams are actively contributing to a wide range of these projects from both a code and technical leadership perspective. To name a few, those efforts include Kubernetes itself, KubeFed, KubeCost, Cluster API, and many more. Due to recent cyber attacks, there has been increased focus on ensuring a reliable, transparent supply chain, especially for open source software. At D2IQ, we provide an opinionated Kubernetes implementation while remaining transparent around each piece of code integrated into our platform. We keep all of the information regarding add-on versions and vulnerabilities associated with each add-on for each major Convoy release in our public-facing documentation. In addition, there is also a list of shared system resources available on our documentation. D2IQ is also a part of Kubernetes embargo community, meaning we are given early builds of Kubernetes under confidentiality to test and package in advance of the official release. This status gives us the opportunity to give you critical CVE patches very quickly. Of course, ensuring security to the best of our abilities underlies in everything we do. D2IQ performs both OSS licensing and container image security scanning for releases. Image vulnerability scanning is performed on a continuous basis as part of D2IQ's standard CI/CD process. Convoy and Kommander distribution are infrastructure agnostic and have a proven track record of running in a variety of environments, including those that are fully air-gapped from the internet. And last but most interesting is FIPS compliance. Today's cybersecurity focuses on reducing the attack surface outside the traditional solutions like firewalls, network segmentation, or system controls. Whether in transit or at rest, your data is vulnerable to attacks from hackers and other malicious actors. That's why protocols like transport layer security are used to help to secure data point to point with data encryption. To establish a secure connection, the TLS protocol requires the selection of a cipher suite and key to encrypt your data. The NIST Cryptographic Module Validation Program provides instructions on conformance testing of cryptographic modules. The assessment covers 11 areas with regards to the design and implementation of a cryptographic module to ensure the overall rating meets your requirements. Using vulnerable cryptographic modules or ciphers can lead to attacks such as bypassing the seeding process used to generate keys, leaving you vulnerable to attacks. This is why rigorous testing and certification is so important. The federal government requires all hardware and software components it uses to meet Federal Information Processing Standards, which is FIPS. Convoy and Kommander are FIPS certified, and government agencies can rest assured that their Day2IQ Kubernetes platform products and workloads have been certified secure by an independent laboratory following government standards. And with that, I will wrap up this presentation. Thank you and have a good day.